So now that we've done a double pendulum, we are ready to look at slider cranks. The triple pendulum video gets us ready for 4 bars. So if we think back to our original drawing, right, we had something that looked like this. So we had B, P, Q, length R1, R2. We had theta, and we had phi. And if you're using an inertial frame, there's our ij. So we spent all this time, and what did we end up with? We ended up with a VQ equation and an acceleration of Q equation. So how do we actually use that for a mechanism? So if you remember back from earlier in class, we looked at mobility or degrees of freedom, and we, using Grubler's equation, determined that a slider crank has 1 degree of freedom, or mobility equals 1. And then what that means is if I either, grab a color here, if I either crank this around, if I crank this around here, the slider will go back and forth. Or like in an engine, if I make the piston move back and forth here, the crank will crank. So I have 1 degree of freedom. So how do we develop the equations for this in general, for any length r, for any initial position that I may have? So let me try to remove some of the stuff I just put on there that's blocking here. Here we go. Okay. So what do we do? So if I look at these 2 pictures, so if I look at my slider crank in condition 1 and I look at my general equation, what do we see? My first link can spin, but Q is constrained. And what do we know about Q? It can only slide in the X direction, and it can't move in the Y direction. So what we're saying is my velocity of the slider is simply equal to VQX from my kinematics table. And then I have a constraint as well that, oh, back to a dead spot, try it again, that VQY equals 0. So what does that look like? We need to find our 2 equations. Well, I copied and pasted them from the old videos here. So what is my VQX equation? Right, if here's my velocity Q, all I need to say, this is equal to VQX. In this case, that's the velocity of my slider. Done. This is my VQY, and that's equal to 0. So let's think about this for a moment. If I look at my picture here, what are all my variables? I have a length R1, I have a length R2. I have an initial angle theta, I have initial angle, sorry, too many dead spots on my screen. Try to move it here. I have phi. I have a theta dot, and I have a phi dot. So let's talk about each one. Right, those are all the variables in my equation, VQX and VQY. And we've said that the velocity of slider is VQX, and I have a constraint that VQY equals 0. So if I have my slider crank in front of me, I can measure R1. So R1 I can measure. R2 I can measure the length. And the length is defined from pin to pin. So not the overall length, but between the joints. So from capital P to Q, I can measure that. If I have a position of the slider crank in front of me at one particular time, I can find the angle. Theta is defined from the horizontal. So let's say looking at it maybe, I don't know, 20, 30 degrees. And what is phi? So keep in mind, as I have it marked here, I'll go over it again. Oops. Grab a pen here. That phi starts at this horizontal and comes all the way around. So So just keep that in mind, right? I'm past 270. I'm probably 300 and something degrees. Or maybe it's, if I want to go negative, like say negative 45 degrees. Just keep that in mind. It's all the way around. So what do I have? Okay. So I have the angle, I have theta dot and phi dot. And as I've said in the previous videos, let's just remember the units there would be radians per time. See if I can clean that up a little bit. Radians per time. So it can be radians per second, radians per hour, radians per whatever, but it's not degrees. When a theta dot is that, or a theta double dot for angular acceleration, or v dot, etc., it's separate. It's always in radians per something. So if you're given the problem in revolutions, let's say revolutions per minute, you need to convert it to radians per minute or radians per second, but it has to be in radians. When a sine of theta, cosine of theta, it doesn't really matter as long as your calculator is set to radian mode or degree mode. It makes no difference. So I have two equations. I have that, again, the velocity of the slider here is equal to vqx minus r1 theta dot sine theta minus r2 phi dot sine phi. And I have my constraint equation that r1 theta dot cosine theta plus r2 phi dot cosine phi equals 0. Two equations. I can handle two unknowns, but I'm missing one thing. I'm missing here in my list what? The velocity of sorry, I keep moving my screen around. The velocity of the slider. So if I have two equations, two unknowns, I need to know one thing. Typically, it's not phi dot, that's the angular velocity of the coupler or the conrod. It is, I typically know the angular velocity of the crank, theta dot, or I know the velocity of the piston. So let's assume I know theta dot. So I have two unknowns, phi dot, still have a spot on the screen, phi dot, and let's see the velocity of the slider. And now I can solve for that. And again, what's the beauty of this is there's your general case for any horizontal slider. I don't care what the length is, I don't care what the angles are. If I can find it in one position, I throw it into I have my two equations, two unknowns, and I keep going. Now, what if I need to know the accelerations? So let's take a look at this original picture here. There we go. So let me blow it up again. That's pretty good. So what do I know? That if I look at my acceleration of the slider, my acceleration of the slider is simply my AQX component. And then I have a constraint, let me get my screen fixed, that says that AQY equals 0. In other words, if I look at point Q here, the piston can't move vertically, so there's no acceleration. So what do I have? Let's scroll back up to the equations we've had in the past. So we're saying here, switching colors back, this, what we derived before, I'm going to find the spot to write it here, equals, right, that was my AQX. But really what I care about is that is the acceleration of my slider. That's what I'm looking for. And similarly here, I now have another constraint. Right, that was my AQY, acceleration at point Q in the y direction, and that's equal to 0. Okay, so let's go back to this master list here. And what does that add? What that adds is now, if I look at my equations, I have now a theta double dot term, that's angular acceleration of the crank. I have a phi double dot term, which is the angular acceleration of my conrod, connecting rod, or coupler. And I have my, sorry, let's keep moving my screen around here. I have the acceleration of my slider, my piston, depending what my problem is. So typically, I'm either looking for the angular acceleration of my crank, or I'm looking for the angular acceleration of the slider. Well, let's think about this, right? I have my two equations already for the velocity, v slider, and my constraint vqy 0, right? So if I use those first, I've now already solved these. So now if I look at my second two equations, my acceleration of slider and my AQY, what are my unknowns? Just theta double dot, phi double dot, and acceleration of slider. Well, I have two more equations now. So I can handle two more unknowns. So let's assume I'm given, let's say theta double dot, I can now, so if I'm given this, I can now solve for these two. Or if I'm given acceleration of slider, I can find my theta double dot. And as before, theta double dot is going to be in radians per some sort of unit of time squared. Same thing for phi double dot. So just as before. So I have this one set of equations, either two equations or four equations, depending whether I'm looking for just velocities or velocities and accelerations. Now, very, very similarly, what do I have in this case 2? In this case 2, all I have is a piston or a slider that's vertical. So what are my equations? Velocity, sorry, gotta work around these dead spots. Velocity of the slider is vqy, just a vertical component, and my constraint is vqx equals 0. Similarly, if I need to know the acceleration of the slider, and get away from momentum there, acceleration of the slider is what? Just aqy, the acceleration at point q in the y direction, and my constraint would be a qx equals 0. So I have those two constraints. So if I scroll back over here, all that changes is that this term here is not 0, becomes the velocity of the slider, and this term here becomes 0. And the same thing with the acceleration. And that's really it. Same number of equations, same number of unknowns. So in the next video, I'm going to focus on this general case here, number 3, where if I want to write one set of slider crank equations, I can use it for everything. So the case would be when beta equals 0, I have the horizontal slider. Spin around again. I have the horizontal slider. When beta equals 90 degrees, I have the vertical slider, or any angle that I choose. So that will be in the next video.